deepfake represents one of the most persistent challenges of our time. While the intention behind generating deepfakes may not always be malicious, but the consequence may be deeply harmful and far-reaching, ranging from misinformation and reputation damage to threats against individual and societal needs. Moreover, creating deepfake is now easier than ever. We just need a good GPU. And available tools are there. People can produce studio quality deepfakes right from their home. This technology is not only confined to Hollywood studios now, it's in the hand of anyone who has a good, decent graphic card. You may have observed that high-profile celebrities and public figures have already become frequent targets, exploited for misinformation, manipulated for fake pornography, or turned into the viral memes.
What we have tried to do is we have taken this problem multi-stage approach, where we have developed a system which tries to optimize the data which is reaching us and then try to hit the problem on the optimized funnel data set. This boils down to multiple stages, where we first allow a user to their identity, give a consent that here is my face, please start tracking it and tell me what is happening with it. We then build a pipeline that any video which is coming in is first broken down into just the faces, the frames which contain faces. These faces are then run through the identity pipeline. The identity pipeline establishes whether one of the platform users is involved in it. And when we say one of the platform users, it may be the platform user who is deepfaked or a person along with the platform user who is deepfaked, because both are equally dangerous. Once this is done, we run the heavier models, which is the actual deepfake detection. No good deepfake model right now does everything. Although something has come up, we'll cover towards the end. But while we started this project, every week we have seen new deepfake models coming out. And to keep up with that itself was quite a bit of work. But we have chosen certain models, and with a combination of 5 different models, which are sensitive to different features and different, let's say, racial identifications as well as facial constructs, we have been able to put an ensemble together that identifies deepfakes up to a good extent. And that, coupled with the entire pipeline of notification and telling the user that they got a hit, is how our platform gives value. So with no further ado, we'll just quickly cover the architecture. How we are planning to do this is in a pipeline of phases. And the reason we have kept these blocks is so that each of these blocks is independently scalable horizontally. The starting point is either a video which is uploaded or monitoring point like a webhook. And when this comes in, immediately and all on near real time, our face detection algorithm runs, which quickly extracts all the frames which have faces in it. Once these faces are pulled and stored into our block storage, the face identification is triggered. This looks for any person belonging to our platform which has been tagged in these frames. If there is a match, then we trigger the heaviest pipeline of our setup, which is the deepfake classification. In this entire process, we involve the database, which is both vector databases for storage of face embeddings, as well as the relational database, which manages our platform's construct and how a user is linked to a face. Along with that, there is block storage, which is equal to S3 or any kind of bucket storage, where the raw video, the extracted frames, and the intermediate frames are stored. Our pipeline and our product in general is fairly heavy because it does media rather than text. And that's why we had to make sure that we optimize it in a form that it runs on any machine. That was quite a bit of work. So therefore, there is the entire of our MLOps or DevOps, which covers the aspect of how we run it everywhere. Last part, least insignificant, is the notification system and the platform itself. The notification is right now using S, which is a generic notification system that can tag and trigger any other notification. So trigger an email, in future have WhatsApp, SMS, anything else. And the platform itself, which is the client application, we have tried to make it mobile responsive and desktop responsive, so it runs everywhere.
With this pipeline, it is the first critical step because that forms the base for the next important critical part and forming the foundation for the downstream system analysis. Its main goal about the face detection is to efficiently and accurately identify and isolate the facial region from the video content. When we started thinking about how do we implement face detection, was the first thing what came in mind is it should find right and it should find fast. This particular step of the face detection, it is actually takes an input video, and divides that into 4 submodules. It is like it starts with video processing, then it goes to the intelligent frame selection, then goes to the face detection piece of it, and then standardize the output, which is used by the next step of our model. Using perceptual hashing, a D-hash with Hamming distances, we filtered out the redundant frames, achieving a 70 to 95% of reduction in the processing the load, while retaining the visually unique frames only. As we can see on the screen, there has been a comprehensive evaluation of models was conducted on comparing the factors like accuracy, FPS, and other key factors, out of which the MediaPipe BlazeFace was selected for because of its exceptional real-time performance, which is close to 20 to 30 FPS, what we have seen while doing the testing around, with the minimal computational load and robustness across different conditions. When we say different conditions, it's around the lightening of the video, how the face are being visible on, is the video taking with a blur or with the clarity. And then I think the last part is to standardize the face image. So in short, this particular model, what we selected, BlazeFace, offers us a superior balance between the face accuracy and the processing speed. And as we can see, this is the first step. Successfully implementing this lightweight, efficient and accurate pipeline provides the necessary input and establishes a strong base for the deepfake detection piece of it.
So I'll be explaining the face indexing, which runs parallel to the face detection pipeline and the face identification module. So for both of these modules, we have used common model. To select on the model, we have tried few of the popular face detection and embedding model. You can see it on the screen. And while evaluating, we have found ArcFace of inside face being the best model, although the GPU utilization is high, but it serves a good robustness along with a good dimension of embedding. So in face registration, what happens is the user provides a MP4 video of his own face from turning from left to right, 180-degree coverage, and from that video, the keyframes are extracted in order to give a diverse data set without any redundancy. And then for each of the frames, face analysis performs embedding. And at the end, all the embeddings are averaged out to create a common embedding, a single embedding, which represents the user's identity. And then the user's identity is sent out to the Pinecone and labeled with the user ID. Moving on to face identification, what happens is the frames whichever are extracted from face detection module are kept in GCS, Google Storage. From there, it picks up each of the faces, embeds it, and sends a query to the Pinecone where the user's embeddings are kept. Finds the matches, adds to a list, and once all the frames are processed from a particular video, it sends the whole list forwards to the deepfake detection. So if in any video of user's face is found, be it deepfake or along with any deepfake face, it catches that and forwards it to deepfake for evaluation if deepfake is available in the video or not.
Ensemble models. So as I said, this is the core part of our pipeline where we have to find out whether the facial video is authentic or not, right? So as Vishut already mentioned, it is our ensemble model, which leverages 5 pre-trained models that are mentioned in the PPT. So just to give, we can see there is a wide variety of models like vision transformers to hybrid models like CrossEfficientViT vision transformer and generic CNN models. So just to give you an idea what is a vision transformer is, it is like a deep, again, similar to a conventional transformer model, but for images, right? So that is essentially what vision transformer is. Coming to each model and why we chose it. So the first two models is completely based on pure vision transformers, where both the architecture uses like multi-headed self-attention layers and feed-forward networks, like conventional, similar to a typical transformer, like an LLM transformer, right? So these two models actually excels specifically in long range, getting the global context of the whole image as such, like unlike the CNN part. So this helps us getting a context of subtle inconsistency in the whole image when compared to a specific part of the image, like just the face or the other part of the body, right? Once this also helps us in understanding the overall pattern of the whole image given. The main difference between the first and the second model is the data set it has been trained on. So there are multiple open source data sets that were available, face forensics and deepfake detection data sets that are very widely used. Based on using these two differently trained models, we are trying to bring in generalization as a generalization to our model. Though I would like to tell that this brings a set of drawbacks as well, since these are very heavy models to run near real time. It is very heavy and takes a bit of time to detect. And this the third model would be again CrossEfficientViT. That is the cross-efficient vision transformer, where it is it's a hybrid model of EfficientNet, that is a CNN, and the vision transformer, where this brings both a mixture of both local context and the global context to say, like it focuses on both image inconsistencies and as well as this one, like the whole image itself. But again, since this is a very complex model, it is also not ideal for real-time scenario. And coming to EfficientNet, it is a CNN based model. It is very good, very light, and performance and speed ratio, right, for real-time performance is very good. And it, as a CNN, it does focus on smaller elements, but again, it is ideal for scenario. But again, it is the accuracy is not as good as the transformer, I would say, but based on what we have tested, but it has been trained on a good data set. So real-time scenario, we did get a good result with this model. Coming to the last model, it is XceptionNet, which is also similar to a CNN model, and this is the lightest of all, and excels in the spatial data, like edge detection and small textural inconsistency, to say. The thing is, with this with all of these models, we have assigned certain weights because we ultimately will be aggregating all the predictions of each model into a single confidence score. So for each of the weights, each of the model, we have assigned certain weights, as you can see, like 23% for the 4 models and 8%. This is solely based on what we have tested on our local data. And even though metrics suggest there is a very good accuracy to bring in the generalization, when we speak about generalization, the models do lag in certain racial aspect or regional aspect as such. So what we have done is, based on our testing, we have assigned all of those weights to each of the model, and that is our ensemble model.
We will quickly try to go towards the demo as we are a bit short on time. So I'll quickly cover how is our deployment architecture, how we have taken forward the actual deployment and fixed it to the infrastructure. We have tried to decouple systems into different parts. One is the part which gets triggered infrequently, which is whenever a video actually shows up, it gets triggered for downloading and storing. The second part is the microservices layer, which is running continuously and taking care of the face detection, identification, and deepfake detection. And then there are the different parts which notify the application which runs to the user, and the entire store where we have the vector store, the relational store, and the entire file store. In order to get into a more detailed version of this, whenever you can think a webhook or an upload is coming in, this is first run through the face detection of frames. These extracted frames are stored to S3. The face identification pulls these raw frames, carries out a vector search by creating an embedding and comparing the vector on cosine similarity. Once it has matched any faces from our platform, that's when it triggers our heaviest pipeline. Pipeline reads to some person being detected from our platform. It triggers an alert that can be seen on the platform. The specification of technologies and details used are over here. In the deployment side, we have tried to ensure that this is a fairly heavy pipeline, and it took a lot of work for all of us to package our codes and our sections into a way that can be run on anything. And that's what we submitted. Simple as code doing, and it'll even work on a 2 virtual core CPU. In fact, we have even benchmarked it on a very small CPU, 8 GB RAM kind of a setup with these specific numbers. We've also added in a Terraform setup, which extends our Kubernetes setup itself, which allows it to run on any platform, running on any cloud, so to say. The key parts are that we have used a microservices architecture so that we can take each of these services, scale them independently. We have used different deployment setups. We also have GitHub Actions tied in so that anytime there's a code changed, it gets deployed automatically. There is near real-time processing. This is mainly because of the GPU overload that is required and a bit of more optimization, which will come over time. But mainly we can handle 60 to 180 frames per second incoming. And the deepfake detection is the heavy part, which runs in the background through our Celery job. On monitoring and scaling, we have ensured we have made it Lambda ready so that if there is a spike, we can deploy it on Lambdas while the consistent infrastructure is running on, let's say, a set of load balance servers. On security, we have used the standard constructs for storing with pre-signed URLs on the buckets and JWT for authentication. We've also put a demo and we have deployed a version of this available, but we will quickly shift to the actual demo of the platform. Our platform itself is a fairly simple one to use. It's meant for users to come index their face and start using it everywhere. Of course, there are edge cases like long things and going beyond and all. These are things we will solve over time. But we will come to the core part of the platform. It all starts with you indexing your face. We have prepared some sample data, but we are ready to use any kind of data effectively. So it all starts with us indexing our face. I'll just show you an example of how this face index works. So in face index requires you to just show all the sides of your face. And it can be a video as simple as this. Once we index this, you will see here this indexing has been triggered. And it has gone ahead, extracted, and stored to Pinecone vectors. In Pinecone, it has stored 35 different vectors of this. So different aspects of the face will get stored, and you will see your face getting indexed over here. We've also put a small consent system and put best practices so that the users are putting the right face. But once this is done, this is where our real platform shines out. So to start with, let me put a very obvious deepfake. I think Vishal's video. Yeah. So while it is I'll just walk through the extraction in this one case. So first thing is the media pipe face detection, blaze face, which gets triggered, extracts all the relevant faces, and then starts the identification. This identification process is going to have the Pinecone vectors, and then it goes ahead and triggers all the models. There are 5 models triggered, and each model takes different amount of time. So we are doing this via the async gatherer, and also which extends to our PyTorch barrier functions. So in this async gatherer, it is going to go ahead, run all the models, and give back a result. So these are still running, and here's the result. So it should shortly update here. Here we go. It's a deepfake. So this is a very obvious deepfake, I would say. So I wouldn't tell this is okay, but yeah, here you go. This is Vishal's face.
I've been thinking about this recently. If I could talk back to that 17-year-old who was doing regional theater in Rochester, I would say.
So for this reason, it has come in as a deepfake. Now, if this was a genuine video, let's say, I think Vishal you have talked about. So Vishal is talking about how deepfakes work, and we'll just go ahead and upload this. This is a slightly longer video, so it will take some time to run. Again, the same process will work. First, it does a face extraction through Blaze face, then goes through the identity of the faces. Once the identity is received and it matches some identity, it's going to run all the 5 models for deepfake detection. As it does this, it's going to keep updating this on the platform as well. You'll keep seeing it. Because we are in a debug mode, we have also put whatever is the latest response over here from our backend. Okay, this is authentic. Great. During our entire setup, the reason we have built this platform is not just because you can be deepfaked, but someone else can be deepfaked in a video with you. And this extends in an example over here where Vishal is with others. Now, his face is his face itself, but someone else has been deepfaked alongside. The other people have been deepfaked. Now, this is where things get tricky because it's the identity detection of a person, but deepfake detection of someone else. Now, the features of deepfakes is what our models are sensitive towards. So it should still get triggered for it and ideally give a result. But this is a slightly bigger and it's an HD video. So this may take a few more seconds. So this was a slightly larger video. It's still through identifying faces. There are 3 different faces, and I think our vector is already stored up these faces, which it should show. Right, we have about 186 faces that are indexed right now. So it's going to take a few seconds. Let it continue over there. So I think you can see now the model 1, model 2, model 3, model 4, and model 5 have been triggered. Here also to detecting the deepfake. This is also a deepfake, which is as expected. Because I have indexed that face, it is showing me that it has detected you. We have already seen how face indexing and detection works. Now, what we want this platform to become is once you have indexed your face, you can connect your accounts. Let's say you want YouTube to be monitored, Instagram to be monitored, anything else to be monitored. We will write services which are bound to these platforms and continuously taking a feed of whatever is happening over there. Anytime there is a video that gets tagged to face, you get notified. Notifications can be managed in the settings where you have the in-app notifications, what you must have seen, and emails, and we can add any number of other things over here. We've tried to make it more platform-ish and a complete version rather than just a prototype. This platform is already mobile responsive, and it can be used on a mobile as well. The QR code, which I've shown earlier, can be opened by you, and you should be able to use it end to end. So this is like the mobile responsive version of it. You get a sidebar to use different things. I would not say the most optimized mobile version, but it's definitely usable over there.